So I think we're back to recording again. All right. So today's lesson is related rates, also known as El Gato de las Nueve Vidas. What does that mean, Spanish-speaking people? The cat with 9 lives. I'm El Gato with 9 lives. Whose house is that? No, that's not my house. Max Bronze's house. Come on, people. Know your classmates. Okay. The cat with 9 lives. So, I was painting Max's house quite a few years ago, and I had this scaffolding up about, this high. That's how high the scaffolding went. Well, I can't get to the top of Max's house, can I? With scaffolding that high. So then I put my ladder on top of the scaffolding, so it went up about, that high. But Mr. Birschbach did not think about physics when he set up that. Because think about this, people. Here's scaffolding. Here's a ladder against the house. As Mr. Birschbach goes up the ladder, what happens? Well, there's a certain force this way of the ladder, which forces this to fall down, which forces Mr. Birschbach to fall down and go boom when Mr. Birschbach was standing about this high on the ladder. Fall down, go boom. At least I had the roof of the porch to fall down onto and not all the way down to the ground. Because I was like way up at window level or a little higher when that happened. Not a fun thing. So there, you know where, those of you who know where this is right across from Flint Field, right? No, there wasn't a baseball game. But there's this, there's that little park just by the parking lot. There's a lady reading a book at a picnic table when Mr. Birschbach went crash, boom, bang. She looked up from her book. I kind of looked at her. She's like, eh. She did not walk over to say, are you okay? Or anything like that. Okay? Now, that's not the only ladder fail I've had. I've had 2 other epic ladder fails. Okay? And you're wondering where I'm going with this? Well, it's Calc class. We can have a little fun. But okay. So there's this tree branch on this tree that I'm cutting. Okay? Cutting this tree branch with, and it goes up like this too. But it just doesn't make this tree look good. So I put my ladder up on this tree, and Mr. Birschbach saws this limb off. Well, I wasn't really thinking about my physics there either. Because when you saw off this tree like this and it falls down and goes boom, this tree, with every force down, there's an equal opposite force up. Well, this limb, once this broke off, it sprung up. Well, it sprung up so high that my ladder wasn't touching the tree anymore. The Mr. Birschbach falls down, go boom, with a running chainsaw in his hand. Ladder, and then there's like a house over here. The ladder falls, because this is trees like close to the house, and that branch is like hitting the roof of the house and stuff. So I needed to get it off the house, and well, yeah, that all happened. Ladder hits the house. I twist, I fall. A little later, work it out. Okay. And then I keep cutting up the rest of the tree branch. Yeah, and I kept painting after that. I reset up my scaffolding and ladder and kept painting later on that day too. So, my third one Third epic fail of ladder and physics. Okay. Epic fail number 3. Okay, I'm on a house. How should I draw this? Okay. So here's the big part of the house. And they have an addition out here with a roof coming kind of up like that. Okay. Well, if you take the side view of what's going on, so here's the addition that goes up. Oh, roof goes up this way. Goes up this way. And then the rest of the house is like here. And so I'm trying to paint around a window here, but I can't get my ladder. There's not enough. Oh, the window's further over. The window's like right here. So I can't put my ladder against the window. I can't put it above the window because there's just not enough room. So I decided to set my ladder up this way, like this. Oh, yeah, that was good. I set my ladder up like this so I could paint back over here. Okay. Well, I put my feet above where it went against the roof. And I was kind of, actually, this is, okay, the roof on this is like flat, like this, and it kind of angles up in every direction. So there's rain gutter here, and that. And so I'm holding the rain gutter and painting. So feet are right here. I'm upholding the rain gutter, painting back like this. But see, the ladder's here and my feet are here. What do you think will happen? Well, natural physics, the ladder will tip down this way because of the fulcrum and the weight. I'm hanging up here like this from the rain gutter, and my feet are up here. And I have to go hand over hand to hand on the rain gutter until I get to this part of the roof so I can get down and actually get to my ladder again. 3 epic fails. 3 times I could have absolutely died while painting because of my epic ladder fails and my poor physics. I didn't think about the physics beforehand. And you're going, why are you talking about this, Mr. Bierschbach? Well, here we go. Related rates goes straight into that. Mr. Bierschbach, again, because only somebody would do this, put a ladder on an icy sidewalk. And I actually have never done this. Okay, I never have put a ladder on an icy sidewalk and had the ladder slip out. That would be just stupidity. Okay. Ladder on an icy sidewalk with the bottom of the ladder sliding away from the house at a rate of 4 feet per second. How fast is Mr. Bierschbach falling down if he's at the top of the ladder, which is when it's 20 feet above the ground? So this is like a super tall, super long ladder, 25-foot ladder. That's a big ladder, okay? So 20 foot up on a house is at the top of a second story. So if the ladder starts going away on the icy slope, okay, or not a slope, but on the icy ground, how fast am I going down? Well, what shape? Wow, I didn't know I could do that. What shape is this? What type of a triangle? A right triangle. So we need to know the lengths of the sides of this right triangle. How do you find the lengths of the sides of right triangles? Pythagorean theorem. So we are going to use formulas today. So c squared equals a squared plus b squared. Now what is c? 25. So this is 25 squared equals a squared plus b squared. What's happening is as we slide down and as we slide out, the sides of the triangle, those two sides are changing. This does not change. It stays at 25 because a ladder like this and a ladder like this is still 25 no matter what. But this side changes, this side changes. So if we're talking about changing as time happens, Taylor, you got to pay attention to this. As we change, we have to do derivatives. Now, we have multiple variables today, all kinds of different variables. And so we're talking about changing of things versus time. So, what's the first derivative of 25 squared? 0. So this is just 0 equals, what's the first derivative of 2a with respect to time? What's the respect of a squared with respect to time? It is 2a dA dt. Okay? Plus, what's b? 2b dB dt. And I said this was dy dt. We'll just make this dB dt. It doesn't matter exactly. It could be x squared plus y squared equals 25 squared. But this is the formula we need to use. Now, it says, Mr. Bierschbach's falling down when I'm 20 feet above the ground and I'm going down. Okay? How fast am I going at the 20-foot mark? Well, Pythagorean theorem. If this is 25 and this is 20, how big is this at that point? Do the Pythagorean theorem really quick. Exactly. So 625 minus 400 is 225. So this is 15. So if this is B and this is A, we go 2 times 15 times, and it tells me how fast the bottom of the ladder is skating out on the ice. It's skating out at 4 feet per second, plus 2 times B, we were told at the start of the problem was 20, and I want to know how fast I'm falling down. Well, that's dB dt. So that's still dB dt. We solve for dB dt. Okay? So 2 times 15 is 30 times 4 is 120. So let's move the 120 to the other side. So negative 120 equals 40 dB dt. And divide by 40. So what is dB dt? Negative 3. So I'm falling at a rate of negative 3 feet per second, or I'm going down at 3 feet per second. Now, that's when the ladder is 20 feet above the ground. By the time it slides out, down, and now I'm at 15 feet above the ground. Because now what about how fast would I be going when I'm 15 feet above the ground? Well, if this is 15, what would this side be? 20, because the ladder doesn't change length. So then we just switch the 15 and the 20 around, and the 4 feet per second stays with the ADT. So 0 equals 2 times 20, because this is now 20, times dAdt is still 4 feet per second. The ladder is not speeding up. We're pretending that it doesn't speed up as it goes out. But my speed of falling is going to speed up. So what will that be? 2 times 15 times dB dt. So 2 times 20 is 40, times 4 is, so I'm at a negative 160 equals 30 dB dt. Divide by 30. Negative what? 5 1/3, basically. So when the ladder is 20 feet above the ground, I'm only falling at 3 feet per second. But by the time I get to 15 feet above the ground, I'm falling at negative 5 1/3 feet per second. So I'm picking up pace, even though the ladder is going at a constant rate away from the house. I'm picking up speed as I go down. Okay? So, all right. So that's where we're getting to by the end of the day. Now we'll see all the steps we take to get there. Okay. So you'll have a section of problems like this. The radius of the base of a cylinder is decreasing at a rate of 9 millimeters per hour, and the height of the cylinder is increasing at a rate of 2 millimeters per hour. At a certain instant, time equals 0. The base of the radius is 8 millimeters and the height is 3 millimeters. What is the rate of change of surface area? We're actually going to solve that at the end, but right now when you have these problems, you're just going to figure out what means what. So this is a surface area at time equals 0. Do we know the surface area at time equals 0? And the answer is no, it's none of these numbers that they gave us, so that is not given. This is the first derivative of the radius at time equals 0. The first derivative is the what? The rate of change. Do they give you the rate of change at time equals 0 of the radius? Yes, they do. What is it? The radius is decreasing at a rate of 9, so it's negative 9. So that radius would be 9. H prime of t is the first derivative of the height. What is the height changing at? 2. Okay? So you have to look whether it's normal or it's a first derivative on which number goes with what. Okay, a person stands at a distance of 18 meters east of an intersection, as depicted in the picture here, and watches a car driving away from the intersection north at 3 meters per second. The function gives the car's distance. So this is a person. The function gives the car's distance in meters north of the intersection at time t. And then we have a certain angle. Okay? And the angle is at 0.7 radians. What's the rate of the change of this angle? So to figure this out, we have to look at the various formulas they give us. Okay? Is this a Pythagorean theorem when we're looking at the angle here? No, that's just when we have sides. So this one would be out. Okay? When we're looking at an angle, if I have the opposite and adjacent, what trig function is that? Tangent. So I'm going to use the tangent formula. So for one of the sections, you're just going to be picking out which formula is appropriate for the related rates. You won't have to solve the formula. Okay? So you'll be going from, as you go through these sections, you'll keep building towards related rates, where first you'll be figuring out what do the numbers mean. Then you'll be picking out which formula works best for that. And then you'll actually get into the related rates problems. So the radius of a sphere decreasing at a rate of 1 meter per hour. At a certain time, the radius is 4. What's the rate of change of the volume? Okay, so we want to use the volume of a sphere formula. Anywhere in this classroom have a volume of a sphere formula given to you? Same place when you guys took geometry, way over there. The volume of a sphere is 4/3 pi r cubed. That is the starting point of our related rates problems. Okay, you start with the formula, the geometry formula for a lot of these. Okay, what's this one going to be for? What's that formula for? Surface area of a sphere. What's this formula for? Pi r squared. Area of a circle. What's this formula for? Circumference of a circle. Okay? They look a little different than there because with related rates, time is always a factor. But those are some of the formulas you see. The radius of a cone is increasing at 10 meters per second. Volume of a cone. Well, if you see volume and cone, what formula are you looking for? Volume of a cone formula. Is that A, B, C, or D on this? It would be D, because the divided by 3 is the 1/3 pi r squared h. Okay? They just look a little bit different. This one deals with slant height with the whole square root. That's the surface area of a cone. Okay, now here we'll actually be starting to solve related rates in very basic format when you get to these problems. Okay, so how do we solve a related rate like this? Well, we have to take the first derivative of both sides. What's the first derivative of the left side? 6x. But is that the variable we're taking the derivative of? No. We have to do it with respect to time. So normally it's just 6x. But now when we do related rates, it's 6x dx dt equals, what do I have to do on the right side? Product rule. X times the first derivative of y, dy dt, plus y times the first derivative of x, dx dt. Now they tell you, well, dy dt is -3. Okay, so I put a -3 in for dy dt. Find dx dt when x equals -6. Well, x equals -6, so we take 6 times -6, and we're looking for dx dt equals x is -6 and y is negative. We don't have y. How are we going to figure out what y is? Because I can't have two variables in an equation and solve for it, can we? How are we solve for y? How are we going to know what y equals? We got to go way back to the original equation and plug -6 into that. So 3 times -6 squared is 36 equals -6 times y. So 108 equals -6y divided by -6. What do you get? Should be what? 18? 18. So y is equal to 18. So now I can stick an 18 in here. I can get my dx dt's together. So -36 dx dt minus 18 dx dt equals, oh, it's -18? Okay, there, -18. So this is a -18, so this is a +18. So then -6 times -3 is 18. So -18 dx dt equals 18. So dx dt equals -1. That's the rate x is changing at that certain point. Okay, let's do a couple more of these. How am I going to take the derivative of this thing? What's the first derivative of 1 over y with respect to t?
No, I'm not saying it.
Come on, you were there. -1 over... Yes, Kendra, absolutely. And if you're going, how'd you get that? Remember, 1 over y is y to the negative first. So it's -1 y to the negative second, because we dropped the power by 1. So it's 1 over y squared, -1 over y squared, equals, what's first derivative of 8? 0, minus, so it's negative, the first derivative of x, 1 dx dt. Okay, so a lot of things disappear there. Okay, we're told that, what did I forget? Dy dt. Okay, so -1 over 0.2 squared times -0.5 equals -1 dx dt, because that's what we're looking for. So if we solve this, we get 0.5 over 0.04, right? Equals -1 dx dt. So it's like 50 over 4, which is 25 over 2, which is 12.5. So dx dt equals negative 12.5. Okay. What if we throw that at you? How do we take the derivative of sine of y with respect to t? Cosine of y dy dt equals negative 5x, first derivative, negative 5 dx dt. Okay, so then, Mr. Shaw, you missed all the fun stuff. They were really amazed by all my lack of physics preparations when I set ladders against houses and stuff. Yeah. And have the landscaping box fall out, and down you go. Yeah. So epic fails of ladders aren't just my area; they're Mr. Shaw's area too. Yeah. All right. So what's the cosine of negative pi? It's negative 1. Because if you think of the unit circle, negative pi is back here. So it's negative 1 times 10 equals negative 5. So negative 10 divided by negative 5 is positive 2. Okay. Related rates. You're kind of getting them now, right? Well, now on to the advanced stuff. Here we go. So if you're not paying attention, Maggie Ingebretson.
I'm actually paying attention today.
Okay, good.
I'm so serious.
Good. If the side of a cube is decreasing at a rate of 9 millimeters per minute, at a certain instant, the side is 19 millimeters. What's the range of change of the volume at that instant in cubic millimeters per minute? Holy smokes. First of all, we got to figure out that I've got to find the volume of a cube. The volume of a cube depends on what? The sides. So if I have a side and a side and a side, the volume of a cube is side cubed. Now, the volume is changing with respect to time. So how do I take the first derivative of this? dv dt equals 3s squared ds dt. It says, what is the rate of change of the volume? I'm looking for dv dt. So I got to fill in the s and the ds dt. Okay? At a certain instant, where the side is 19 millimeters, well, this is 19 squared then, right? And it's changing at a rate of, decreasing at a rate of 9, so it's negative 9. There. So you just do the math and figure out the number. Which number is it? It is A. Okay? So just being able to set up the formula is the big part. The side length of a square is increasing at 15 millimeters per second. So a square is a side by a side. What change of area of a square? Well, the area of a square equals side squared. So how do you take the first derivative of that? dA dt equals 2s ds dt. So then rate of change of the area of a square, so dA dt is what we're looking for, equals 2 times 22 times positive 15, which is, I don't know, 660, yeah. Okay. A sphere, and we're talking about surface area, not volume. So the surface area, the area of a sphere, is 4 pi r squared, right? So dA dt is equal to 8 pi